The question of possible life beyond Earth is one of humanity's most enduring inquiries. It is a query that transcends science, touching the very core of our philosophy and our place in the cosmos. When we look up at the night sky, we are not merely seeing points of light. We are witnessing the architecture of our own galaxy, the Milky Way, a single island of stars in an ocean of unimaginable vastness. We now understand that the observable universe contains more galaxies than there are grains of sand on every beach on Earth. The scale is staggering. It is within this immensity that we must frame our search. We're not looking for a single anomaly, but pondering the potential for life across trillions upon trillions of worlds. In 1961, astronomer Frank Drake attempted to bring mathematical structure to this question. His famous equation is not a solution, but a framework for inquiry. It begins with the rate of star formation and multiplies through a series of probabilities, the fraction of stars with planets, the number of those planets that could support life, and crucially, the fraction on which life actually arises. Our challenge is profound. To date, we have but a single data point, Earth. It is as if we are trying to comprehend the entirety of an ocean by examining a single drop of water. Yet, what an instructive drop it is. The evidence, etched in stone, tells us that life on Earth emerged with remarkable speed. Fossilized structures known as stromatolites, found in places like Western Australia, confirm that life was thriving some 3.5 billion years ago. Given that Earth itself is 4.5 billion years old, this suggests that life took hold within a mere few hundred million years of the planet's formation, a blink of an eye on the cosmic scale. This rapid emergence implies that the genesis of life may not be an improbable fluke, but a natural process given the right conditions. Furthermore, the fundamental building blocks of life are not unique to our world. They are forged in the cosmic furnaces and delivered throughout the galaxy. The Murchison meteorite, which fell to Earth in 1969, was found to contain over 70 different amino acids. Only 20 are used by life as we know it. Nature, it seems, is prolific in its production of life's raw materials. Indeed, our radio telescopes have detected a rich inventory of organic molecules throughout interstellar space. Vast clouds of gas and dust, such as the Sagittarius B2 cloud near the galactic center, are veritable chemical factories. They contain complex molecules, including vast quantities of ethanol. While this cosmic cocktail is far from potable, its existence demonstrates that the universe is pre-equipped with the necessary chemistry for life. The search for life beyond Earth has moved from speculation to empirical science, largely due to one monumental discovery. We are no longer alone in our certainty of other worlds. Just a few decades ago, we knew of no planets beyond our solar system. Today, thanks to missions like Kepler and TESS, the Transiting Exoplanet Survey satellite, we have confirmed the existence of over 5,500 exoplanets, with thousands more awaiting verification. The primary method of discovery is a testament to human ingenuity, the transit method. As a planet passes in front of its host star from our point of view, it causes a minuscule but detectable dimming of the star's light. This tiny eclipse reveals the planet's size, its orbital period, and, with advanced spectroscopy, even the composition of its atmosphere. Among these distant worlds, we have found candidates that ignite the imagination. Kepler 452b, for instance, orbits a Sun-like star within its habitable zone, the region where temperatures could allow liquid water to exist on a planetary surface. It is 60% larger than Earth, with a year of 385 days. A world that in some respects feels almost familiar. Then there is Proxima Centauri b, orbiting the nearest star to our own Sun, a mere 4.2 light-years away. In the vastness of the galaxy, this is our next-door neighbor, yet the gulf remains incomprehensible. 25 trillion miles. A journey that would take our fastest spacecraft tens of thousands of years. But we need not look only to the stars. Some of the most promising abodes for life may be right here, in our own celestial backyard. Europa, an ice-clad moon of Jupiter, is a world of profound promise. Geological evidence and magnetic field interactions strongly suggest the existence of a vast, global ocean beneath its frozen crust. An ocean that may contain twice the volume of all Earth's seas combined. The energy that maintains this liquid water does not come from the distant sun, but from within. Tidal heating, the constant gravitational flexing imposed by Jupiter's immense pull, generates enough friction to warm Europa's core. Where there is liquid water and a persistent energy source, the possibility of life must be considered. Enceladus, a small moon of Saturn, presents an even more compelling case. The Cassini spacecraft witnessed plumes of water vapor and ice erupting from fissures near its south pole. When Cassini daringly flew through these geysers, its instruments detected not only water, but also complex organic molecules and silicon nanoparticles, telltale signs of hydrothermal activity on the seafloor. This is of significant significance. On Earth, deep-sea hydrothermal vents are oases of life. Entire ecosystems thrive in absolute darkness, deriving energy not from photosynthesis, but from chemosynthesis, the oxidation of chemicals dissolved in the vent fluids. If similar processes are occurring on Enceladus, the recipe for life may be complete. Mars, of course, has long been the focus of our interplanetary searches. While the romantic visions of a canal-building civilization have faded, a more compelling narrative has emerged. Mars was once a different world. River valleys, lake beds, and specific mineral deposits attest to a time, some 3 to 4 billion years ago, when Mars had a thicker atmosphere, a warmer climate, and liquid water flowing across its surface. The Perseverance rover, now exploring the ancient river delta within Jezero crater, is tasked with collecting samples for eventual return to Earth. These rocks, the first ever retrieved from another world, may hold the ultimate prize: fossil evidence of ancient Martian life. Even if Mars proves to be barren, its past habitability is a profound revelation. It signifies that in our solar system alone, the conditions for life emerged on at least 2 separate worlds. When we include the oceanic moons, the number of potential habitats grows significantly. The search, however, extends beyond microscopic life. We also listen for intelligence. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for over 60 years, seeking a signal that is indisputably artificial. The famous WOW signal, detected in 1977, remains an enigma. A powerful, narrow-band radio burst that aligned with our expectations, but was never heard again. Today, our concepts of detectable intelligence have expanded. We now consider technosignatures, evidence of technology that could alter a star's light, such as hypothetical megastructures, or the atmospheric pollution of an industrial civilization. The discovery of the interstellar object Oumuamua in 2017, with its unusual shape and acceleration, prompted serious scientific debate about its origins, including the remote possibility it was an artifact. While natural explanations are more likely, the very fact the discovery of extremophiles on our own planet has fundamentally rewritten the criteria for habitability. We once believed that sunlight was the indispensable engine of life, that without the process of photosynthesis, complex ecosystems were an impossibility. This paradigm was shattered in 1977. The research submersible Alvin, exploring the depths of the Pacific Ocean near the Galapagos Islands, made a discovery that would revolutionize biology. At the bottom of the ocean, in perpetual darkness and under crushing pressure, they found not a barren wasteland, but an oasis. Hydrothermal vents, spewing mineral-rich, superheated water, were surrounded by thriving communities. Giant tube worms, blind crabs, and unique species of fish, an entire ecosystem deriving its energy not from the sun, but from the Earth itself, from chemosynthesis. This single finding expanded the cosmic real estate for potential life immeasurably. Suddenly, the ice-covered moons of the outer solar system, with their subsurface oceans, transformed from frozen wastelands to prime candidates for biological inquiry. One must now consider that there may be more habitable environments in the hidden oceans beneath the surfaces of moons than on the surfaces of planets themselves. Consider the Jovian system. Jupiter's 4 large moons, Io, Europa, Ganymede, and Callisto, are worlds of fire and ice. At least 3 of them are now believed to harbor these subsurface seas. In the Saturnian system, Enceladus and Titan are joined by possible oceans on Dione and Mimas. Even the distant moons of Uranus and Neptune may hold these secret liquid worlds. Our tools for investigating these possibilities are growing more powerful. The James Webb Telescope, launched in December 2021, represents a quantum leap in our observational capabilities. Its primary mission includes the spectroscopic analysis of exoplanet atmospheres, hunting for the subtle chemical fingerprints known as biosignatures. Oxygen, in large and persistent quantities, is a primary target. On a lifeless world, oxygen is a reactive gas that quickly becomes bound up in rocks. Its sustained presence in an atmosphere often requires a biological source to replenish it. On Earth, before photosynthetic organisms evolved, our atmosphere was virtually devoid of free oxygen. However, the search is fraught with complexity. We must be vigilant against false positives. Oxygen can also be produced abiotically. Ultraviolet light from a star can split water vapor, releasing oxygen. Therefore, we search for chemical disequilibrium, for combinations of gases that should not coexist for long without a continuous biological source. The simultaneous presence of oxygen and methane is one such compelling signal, as methane is rapidly destroyed in an oxygen-rich environment. The case of phosphine in the atmosphere of Venus is a perfect illustration of this intricate detective work. On Earth, phosphine is a gas produced either by industrial processes or by anaerobic microbes. When astronomers announced its detection in the cloud decks of Venus in 2020, it ignited a firestorm of debate and excitement. The surface of Venus is a hellscape, a crushing 450 degrees Celsius inferno under clouds of sulfuric acid. But high in its atmosphere, at an altitude of approximately 50 to 60 kilometers, the temperature and pressure are remarkably Earth-like. Could microbial life persist there, floating in the acidic haze? The phosphine detection remains controversial. Some scientists question the data itself, while others propose novel geological or chemical processes that could produce it without biology. This is the scientific method in action. A claim is made, evidence is scrutinized, hypotheses are tested and refined. In the search for life, we cannot afford to be anything less than meticulous. Venus itself stands as a stark warning of planetary evolution. It may have once been a world not unlike early Earth, possibly even with oceans of its own, but a runaway greenhouse effect, a feedback loop of warming leading to more water vapor, leading to more warming, transformed it into the scorched world we see today. It is a sobering reminder of the delicate balance that maintains a planet's habitability and of our own fortune here on Earth. The very concept of the habitable zone was first proposed by Harlow Shapley in 1959. For our Sun, this Goldilocks zone extends roughly from the orbit of Venus to just beyond the orbit of Mars. But we now understand this zone is not static. As stars age and brighten, their habitable zones migrate outward. In approximately 1 billion years, our own Earth may find itself on the inner edge, growing too hot for liquid water, while Mars may enter a more temperate phase. Our galactic neighborhood is dominated by red dwarf stars. These small, cool stars make up about 75% of all stars in the Milky Way. Their habitable zones are consequently much closer. A planet orbiting within this zone would complete a year in a matter of days or weeks. But proximity brings challenges. Such a world would likely be tidally locked, with one hemisphere in perpetual daylight and the other in endless night. Furthermore, red dwarfs are often prone to violent stellar flares, which could bathe nearby planets in sterilizing radiation. Yet even these obstacles may not be insurmountable. A thick atmosphere could effectively redistribute heat from the day side to the night side. And as we have learned from Extremophiles, certain life forms possess remarkable resistance to radiation. Life, once it gains a foothold, demonstrates a tenacious will to persist. The question of how life begins, abiogenesis, remains one of the most profound mysteries in all of science. The famous Miller-Urey experiment in 1953 provided a monumental first step. By simulating the conditions of the early Earth with water, methane, ammonia, and hydrogen, and introducing electrical sparks to mimic lightning, they demonstrated that the building blocks of life, amino acids, could form spontaneously from inorganic precursors. It was a stunning revelation. The universe, it seemed, was predisposed to creating the raw materials of biology. But there is a vast chasm between a soup of amino acids and the simplest self-replicating cell. How did the first genetic code emerge? How were these molecules encapsulated within protective membranes? One compelling hypothesis is the RNA world. This theory suggests that before the evolution of DNA and proteins, life was based on RNA molecules. RNA is unique. It can both store genetic information, like DNA, and catalyze chemical reactions, like a protein. The discovery of ribosomes, RNA molecules that act as enzymes, lends significant credence to this idea. Perhaps in a warm little pond, as Charles Darwin once mused, or at a deep-sea hydrothermal vent, the first self-replicating RNA molecules began their work, and the grand experiment of life was born. The rapidity with which life appeared on Earth is itself a clue. If life arose quickly once conditions became suitable, it suggests that the emergence of life may be a probable event, given the right ingredients and environment. But if it required a fantastically unlikely series of coincidences, then we may be truly alone. This line of reasoning brings us to one of the most famous questions in science: the Fermi Paradox. Named for the physicist Enrico Fermi, it highlights the stark contradiction between the high probability of extraterrestrial civilizations and the utter lack of any evidence for them. Fermi's simple, devastating question was, where is everybody? Pause 3 seconds. The proposed solutions to this paradox are numerous, and each carries its own implications. Perhaps life is common, but the evolution of intelligence is exceedingly rare. After all, life existed on Earth for over 3 billion years before anything resembling human intelligence evolved. Perhaps intelligent civilizations inevitably reach a technological precipice, a nuclear age, a climate crisis, an artificial intelligence singularity, and destroy themselves. A sobering thought in our own era. Perhaps they are out there, but choose not to communicate, adhering to a principle of non-interference. The recent discovery of interstellar objects passing through our solar system has introduced a fascinating new dimension to the debate on life's origins. The arrival of Oumuamua in 2017, an object with a peculiar elongated shape and an unexpected non-gravitational acceleration, compelled scientists to consider all possibilities, including the remote chance that it was an artifact of an alien technology. While subsequent analyses suggest natural explanations are far more likely, the very fact that such a hypothesis was seriously entertained marks a shift in our scientific readiness. This event revitalized an ancient idea known as panspermia, the theory that life or its fundamental building blocks could be distributed throughout the galaxy, hitching rides on asteroids, comets, or even interstellar dust. It is a captivating notion. Perhaps life did not originate on Earth at all, but was delivered here from elsewhere. There is, in fact, intriguing evidence that supports at least the possibility of interplanetary panspermia within our own solar system. We have identified meteorites on Earth that were unequivocally blasted off the surface of Mars by ancient asteroid impacts, which later journeyed through space and fell to our planet. Remarkably, laboratory experiments have demonstrated that certain hardy bacteria, nestled deep within the protective confines of a rock, could potentially survive the immense radiation and vacuum of space for the duration of such a journey. A compelling demonstration of this resilience occurred on the International Space Station. In a landmark experiment, bacteria known as Deinococcus radiodurans were exposed to the harsh environment of space for 3 full years. Shielded only by the outer layers of the experimental module, they endured the complete vacuum, extreme temperature fluctuations, and relentless bombardment of cosmic radiation. Yet, when brought back inside, they revived. If such organisms can survive that, then the concept of life traveling between planets is not merely science fiction. However, panspermia, while explaining the potential spread of life, only pushes the fundamental question further back in time and deeper into space. It still requires life to have begun somewhere. And the conditions of the early universe were profoundly different from what we observe today.
For the first several hundred million years after the Big Bang, the universe was a simple, elemental place. There were no planets, for there were no heavy elements with which to build them. The first stars were colossal behemoths, composed almost entirely of hydrogen and helium. They lived fast and furious lives, burning through their nuclear fuel in only a few million years before ending their existence in cataclysmic supernova explosions. It is in these stellar furnaces and in the violent deaths of stars that the story of our existence truly begins. These supernovae forged the heavier elements: carbon, oxygen, nitrogen, iron, all the essential ingredients for rocky planets and for life itself, and then scattered them across the cosmos like seeds. Our Sun is considered a third-generation star, its composition enriched by the remnants of multiple previous stellar generations. Every atom of oxygen we breathe, every particle of carbon in our bodies was forged in the heart of a long-dead star. We are, as the astronomer Carl Sagan so eloquently stated, made of star stuff. This realization leads to a profound and somewhat metaphysical concept known as the anthropic principle. This is the observation that the fundamental constants of the universe, the strength of gravity, the force binding atomic nuclei, the mass of an electron, appeared to be exquisitely fine-tuned to allow for the existence of life. If gravity were slightly stronger, stars would burn too fiercely and too briefly. If the strong nuclear force were marginally weaker, hydrogen would be the only element, and complex chemistry would be impossible. If it were slightly stronger, all the hydrogen in the early universe would have fused into helium, leaving no water and no long-lived stars like our Sun. Some interpret this apparent fine-tuning as evidence of design, a universe crafted with a purpose. Others propose a more naturalistic, if staggering, explanation: the multiverse. This theory suggests that our universe is but one of a vast, perhaps infinite ensemble of universes, each with its own unique set of physical constants and laws. We, of course, find ourselves in one of the rare universes where the conditions are just right for life to arise, because we could not exist in any of the others. It is a concept that straddles the boundary between established science and fundamental philosophy. The methods of our search for life are evolving in tandem with our technological capabilities. While traditional SETI has focused predominantly on the radio part of the spectrum, we are now expanding our listening post to include other potential technosignatures. Optical SETI searches for powerful directed laser pulses that could be used for communication. Other scientists propose looking for signs of industrial activity, such as artificial atmospheric pollution in the spectra of exoplanets. There is even the ongoing search for Dyson spheres, hypothetical megastructures that an advanced civilization might construct around a star to harness its total energy output. The Breakthrough Listen project, the most comprehensive SETI search in history, embodies this new multifaceted approach. It is systematically observing millions of stars across a wide range of radio frequencies, and is also targeting the central regions of galaxies where the density of stars might make interstellar communication more feasible. But this ambitious search raises a consequential question. What protocols are in place should we actually detect a confirmed signal? The International Academy of Astronautics has established a set of post-detection guidelines. The first step would be to verify the signal beyond any reasonable doubt, ruling out terrestrial interference or instrumental error. Following verification, international bodies such as the International Astronomical Union and the United Nations would be notified. A key principle is that no response should be sent without extensive international consultation and consensus. The reality of such a moment, however, would likely be far less orderly than these protocols suggest. The impact on human civilization would be instantaneous and profound. Every religion, philosophy, and worldview would be challenged to incorporate this new cosmic reality. Are such beings part of a divine creation? Do they possess souls? For billions of people, these would not be abstract questions, but matters of deep spiritual significance. Even for the non-religious, the philosophical implications would be staggering. Our entire understanding of intelligence, culture, and our place in the cosmos would be irrevocably altered. And then arises the formidable challenge of communication. If we were to detect a signal from a star system 100 light-years away, any form of conversation would be an exercise in profound patience. We would send a message and then wait 200 years for a reply. Entire civilizations on Earth could rise and fall in the interval between a single greeting and its response. The content of such messages presents another layer of complexity. How does one communicate with a consciousness that may have evolved along a completely different trajectory, that may perceive reality through entirely different sensory modalities? Mathematics and physics are often proposed as a universal language. The value of pi, the sequence of prime numbers, the emission spectrum of the hydrogen atom, these are constants that should be the same everywhere in the universe. But beyond these foundational concepts, true understanding may be difficult or even impossible to achieve. Consider the sheer diversity of life that could exist. On Earth, despite our common biochemical basis, we see organisms that thrive in boiling water, in solid ice, in concentrated acids, and in crushing depths. If life on a single planet can exhibit such variety, one can only imagine the forms that might evolve on worlds with different gravities, atmospheres, and energy sources. The discovery of extremophiles has systematically dismantled our preconceptions about where life can persist.
In the grand cosmic drama, comets and asteroids have long been cast as the harbingers of doom. The cataclysm that ended the reign of the dinosaurs 66 million years ago is a stark testament to their destructive power. But a more nuanced understanding reveals these wandering celestial bodies in another, far more creative light. They are the universe's delivery system, the couriers of life's essential ingredients. The European Space Agency's Rosetta mission, which in 2014 achieved the monumental feat of landing a probe on the comet 67P Churyumov-Gerasimenko, provided profound insights. It discovered that the water ice on the comet possessed a deuterium to hydrogen ratio strikingly similar, but not identical, to that found in Earth's oceans. This suggests that a significant portion of our planet's water, the very solvent of life, may have been delivered by a bombardment of comets in the early solar system. But it is not merely water that these icy travelers carry. They are rich in organic compounds. The Stardust mission, which returned samples from Comet Wild 2 in 2006, found within them glycine, the simplest amino acid. This was a direct and powerful connection. The fundamental building blocks of biology, forged in the depths of space, can be transported to nascent worlds. If life did not originate on Earth, perhaps it was seeded by these ancient icy visitors from the outer solar system, or even from interstellar space. This concept, known as panspermia, is not a modern invention. It was first proposed over 2.5 millennia ago by the Greek philosopher Anaxagoras, though he lacked the scientific framework to support his vision. Today we test its plausibility in laboratories and in space. Experiments exposing hardy microbes to the simulated vacuum and radiation of space have shown that some, if protected within cracks in rock or shielded by dust, can indeed survive for years. Imagine a fragment of rock blasted from a wet world like early Mars by an asteroid impact, carrying within it a dormant colony of bacteria. This fragment drifts for millennia through the interstellar void, a silent arc, until its trajectory intersects with a new, promising world, a young Earth. Upon crash landing, the survivors awaken, and a new evolutionary journey begins. Panspermia, however, is not an answer to the ultimate question. It is a potential mechanism for life's distribution. It simply pushes the question of origins back a step and farther out into the cosmos. Where did that first spark of life ignite? Some researchers look to the prebiotic soup of early Earth, energized by volcanic heat or lightning strikes, as in the classic Miller-Urey experiment. Others point to the intricate structures of clay minerals, which can act as templates and catalysts, organizing simple organic molecules into more complex structures. There are even theories that delve into the bizarre realm of quantum mechanics, suggesting that the probabilistic, non-local nature of the subatomic world may have played a role in the emergence of the first self-replicating systems. The debate surrounding life's origins is vigorous and ongoing. One school of thought, often called the rare earth hypothesis, argues that the emergence of complex life requires a highly specific and unlikely sequence of events. This includes not only the right mix of elements and a stable orbit within the habitable zone, but also a large moon to stabilize the planet's axial tilt, like our own moon, which was formed from a colossal impact with a Mars-sized body over 4 billion years ago. Without such a stabilizer, a planet's seasons could become chaotic, its climate oscillating wildly between global ice ages and scorching heat, making the long, stable environmental conditions necessary for complex evolution nearly impossible. Critics of this view counter with the sheer, overwhelming power of statistics. They point to the Copernican principle, suggesting that Earth is not special or unique. With trillions of planets likely existing in our galaxy alone, even the most improbable of events becomes inevitable if you have enough opportunities. It is akin to the odds of drawing a royal flush in a game of poker. For one hand, it is highly unlikely, but over millions of games, it is a certainty. Our own moon's influence on the development of life on Earth is profound and often underappreciated. The tides it generates may have been crucial for mixing nutrients in the early oceans, and perhaps even provided the impetus for life to make the monumental transition from sea to land. Consider the evolutionary pressures imposed by the lunar cycles. To this day, countless marine animals synchronize their reproduction with the full moon, using the higher tides to ensure the safer dispersal of their spawn. On a world without a large moon, how would biology adapt? Evolution might proceed at a different pace, or life might develop reproductive strategies we can scarcely imagine. The implications of discovering life beyond Earth, even in its most basic form, would be transformative for humanity. Consider the Europa Clipper mission, scheduled to launch in the coming years. While it will not land, it will conduct dozens of close flybys of Jupiter's enigmatic moon, passing through the plumes of water vapor erupting from its icy crust. Its sophisticated instruments will analyze these plumes for salts, organic molecules, and even potential biomolecules. If it were to detect something unambiguous, such as amino acids that show a chiral bias skewed towards left-handedness as they are in Earth's life, it would irrevocably rewrite our understanding of biology. We would know with certainty that life is not a one-off miracle confined to our pale blue dot. Philosophically, such a discovery could unite humanity under a shared sense of cosmic kinship. Alternatively, it could spark new divisions and fierce debates over how to proceed. Should we attempt to make contact,
Or should we impose a strict quarantine to preserve these alien ecosystems from contamination? This introduces the critical ethical dimension of exploration. The Outer Space Treaty of 1967 explicitly prohibits the contamination of other celestial bodies with Earth life, a concept known as forward contamination. But achieving absolute sterilization is a formidable challenge. Our rovers, including Curiosity and Perseverance, carried microbial stowaways despite our most rigorous cleaning procedures. If we one day find life on Mars, a paramount question will be, how do we determine if it is truly native and not a hitchhiker from a previous mission? The reverse scenario, backward contamination, presents its own set of risks. The prospect of bringing back samples from another world, such as the cache of rocks being collected by the Perseverance rover, necessitates the most stringent safety protocols. The Apollo astronauts were quarantined on their return from the Moon, a measure that now seems almost quaint. For Martian samples, the containment procedures will be far more extreme, designed to prevent any potential, however remote, of introducing an alien biological agent to Earth's biosphere. These concerns tie into the broader, more profound questions about our place and our responsibilities in the universe. If life is common, does that diminish our significance, or does it elevate us as conscious participants in a grand cosmic tapestry of life? The late physicist Stephen Hawking issued a stern warning, suggesting that actively attempting to contact advanced alien civilizations might be unwise, comparing it to the Native Americans encountering Christopher Columbus, a meeting that did not end well for the natives. Others, like the pioneering SETI astronomer Jill Tarter, advocate for a more optimistic view. She argues that any civilization capable of achieving interstellar travel or communication would necessarily have learned to overcome its own inner demons, its aggressive and self-destructive tendencies, in order to survive long enough to reach such an advanced technological stage. It is a spectrum of perspectives, each with its own compelling logic, and each holding up a mirror to our own human flaws and potentials. Current discoveries continue to shake the foundations of our understanding and guide the future of our search. The TRAPPIST-1 system, discovered in 2017, is a captivating example. Located just 40 light-years away, it features 7 Earth-sized planets orbiting a cool red dwarf star. 3 of these worlds orbit firmly within the star's habitable zone, with the potential for liquid water. However, due to their proximity to their star, they are likely tidally locked, with one hemisphere in perpetual blistering daylight and the other in endless frozen night. Yet climate models suggest that habitability may still be possible. Strong atmospheric winds could circulate heat from the day side to the night side, creating a narrow temperate band along the terminator line, the twilight zone between eternal day and eternal night. Life on such a world might cluster in this perpetual dusk, adapted to the low light levels. It is easy to imagine that bioluminescence would be the norm rather than the exception, a necessary adaptation for communication and survival in a world without a sunrise or sunset. Computer simulations play an increasingly vital role in this preparatory science. Sophisticated models of planetary climates, like those developed at NASA's Goddard Institute for Space Studies, predict how atmospheres evolve under various conditions. For TRAPPIST-E,